Hey everybody, this is the Gothic Chess King, and this video right here is the solution to a math puzzle that I had originally published on LinkedIn in 2016. I put it up here on Twitter, and after quite a few people reviewed the puzzle, they said there was no solution, that it was impossible, and in general it was BS. Well, it's a tricky little puzzle. You have to know quite a few things to be able to solve it, and there is a unique solution. The first two equations you see up here show that the sum of two unknowns is 4 and their product is 8. This is a standard problem that could normally be solved just by using the quadratic equation. However, the third equation there throws an interesting twist in there. It says apple cubed minus pear cubed is 2 to the 5th e raised to the power of pi I over 2, which means there's a complex valued solution. Complex numbers that have the number I, where I equals the square root of -1, are a little more notorious to solve, and the quadratic equation usually has a negative number in the square root, which is why the number I appears here. So you actually need all three of these equations, even though there's only two unknowns. And as we go through the problem, you'll see why. Okay, the first step is, what information do you need to be able to solve this problem? Obviously, the first part is you have to know how to apply the solution to the quadratic equation. The other thing you need to know, as I alluded to, was I squared equals -1. Again, how to use complex numbers in your solution for quadratics that have a negative number in the radical. In general, you have to know how to multiply complex numbers as well. In this case, the solution will involve a complex conjugate pair of the form a plus bi and a minus bi. Because of the third equation in this puzzle, you need to know how to cube a binomial. And I'll show you how to do that. Because the number e is in there, I just put this in here for background information. E is actually the continuing compounding interest solution. If you have interest that is accumulating and being compounded continually, if you evaluate the expression, the limit as n goes to infinity of 1 plus 1 over n raised to the nth power, you'll get the number e, which is approximately 2.71828, and it repeats indefinitely. The fifth piece of information you need is where quite a few people stumbled. E raised to the power I theta, where theta is in radians, is the cosine of theta plus I times the sine of theta. Not too many people know that. Every electrical engineer on the planet knows it. We use that quite often in solutions to electrical engineering problems. It's really a beautiful equation, how it takes the exponential function in the complex plane and can actually map it to integer solutions, which didn't apply here, but in general you can e raised to the power 2 pi I, for example. E raised to the power of pi I is -1, 2 pi I is +1, which again is something that's extremely unusual. So to start with, I changed the apple and the pear to the letters A and P, just for the sake of brevity. Notice equation 3, a cubed minus p cubed equals 32 e to the pi I over 2. All I did was convert 2 to the 5th to 32. Going back to equation 1 and getting rid of the pear and just solving for the apple by itself, apple equals 4 minus p. So again, that's nothing unusual. You plug that back in to equation 2 where the product is created and you get a quadratic. Okay, all you do is substitute 4 minus pear in for apple, and you have 4 minus pear times pear equals 8. So you have 4 pear minus pear squared equals 8. And when you rearrange the terms to make it look like the form of the quadratic equation, I'm calling this equation 5 now, minus pair squared plus 4 pair minus 8 equals 0. Now we had the quadratic equation in terms of x. If you just substitute the letter p for the letter x, we can derive what it would be for the pair. Pair equals minus b plus or minus the square root of b squared minus 4ac. That entire expression divided by 2a. And because we had already rewritten equation 5 in the right form, we can derive the coefficients. A is minus 1, b is plus 4, c equals minus 8. And now we're just going to tactically go through step by step and solve for the pair. And you can see all that was done here in these steps was plugging those coefficients into the quadratic equation and combining terms, reducing. Notice we have the square root of 16 minus 32, which is the square root of negative 16. Well, that's where the I comes in. The square root of negative 1 is I. So the square root of 16 is 4. So the square root of negative 16 is going to be plus or minus 4i when you use it in the form of the quadratic equation. When you simplify everything, you'll find pair equals 2 plus or minus 2i. Now the trick to this problem is if you go back to equation 4 and make the substitution that apple equals 4 minus pair, 4 minus pair, 4 minus equation 6 will give you equation 6 again, which is also equation 7. Apple equals 2 plus or minus 2i. So right now, the conundrum is both apple and pear are exactly the same. And the problem is asking you to determine which one is which is the entire reason why you need the third equation. Okay. And here, again, even people who had gotten to this point, they didn't know how to proceed. They didn't know how to disambiguate, when all you really need to do is cube 2 plus 2i and 2 minus 2i and just plug them into the equation, trial and error, and determine which one has to be the apple and which one has to be the pear. So that's what we're doing here. First thing that you have to do, though, is apply e to the I theta equals cosine theta plus I sine theta in the case where theta equals pi over 2. The cosine of pi over 2 is 0. Of course, that's the cosine of 90 degrees. The sine of 90 degrees is 1. So e raised to the power pi I over 2 is just I. Again, this is something that's well known to electrical engineers. It's the complex valued exponential just rotates around the unit axis in the complex plane. But we'll forego that discussion and just say equation 8, apple cubed minus pear cubed equals 32i. So, as alluded to previously, all we need to do is perform the cubes and see which one solves the original condition. People who might have forgotten how to do a binomial expansion for higher powers can use this technique referred to as Pascal's triangle. Pascal came up with this clever idea of just writing out the coefficients for lower powers and using a little trick to determine what the coefficients are as the powers increase. So if you look right here, you see for power 0, a plus b raised to the 0 power is just 1. Of course, anything raised to the 0 power is 1. Even if you have two terms added together, it's going to be 1. A plus b to the first power, the coefficients of a to the first and b to the first are just 1 each. Once you square the quantity a plus b, there's going to precipitate out a middle term. A plus b squared is not a squared plus b squared. It's a squared plus 2ab plus b squared. And it's something you could easily convince yourself of just by plugging in a couple of numbers. When you get to the power of 3, it gets a little more complex. A plus b to quantity cubed is a cubed plus 3a squared b plus 3b squared a plus b cubed. And I'll explain that on the next page. So these coefficients modify, and they're color-coded here. The 2 modifies the A times B term. The 2 3s in the light blue modify A squared B and AB squared. And likewise for the other color-coded entries, the 10 modifies A times A times A times B, which is A cubed B squared, etc. So here's the way you actually go about determining what the coefficients are. You can see up here, the 2 in green is formed by adding above it 1 plus 1. Okay, and that's diagrammed down here. 1 plus 1, boom, you put the 2 in there. Now when you go to the third power, you're going to add 1 plus 2, and then down comes 3. 2 plus 1, down comes 3, and then just put a 1 to the next of it, to the next of the 3. And that's kind of shown here. The fourth power, you do the same thing. The 1 plus 3 is going to give you a 4 for a coefficient. 3 plus 3 is going to accumulate to a 6. Then you have 3 plus 1, the mirror image is 4 again. So that's how these coefficients are determined. They're just the sum of the 2 nearest neighbors in the prior power. Okay. So this page shows the expansion of a plus b to the 0 power through a plus b cubed. And you can see, again, a plus b cubed is a cubed plus 3a squared b plus 3b squared a plus b cubed. Now, we're interested in 2 plus 2i being cubed, and then later 2 minus 2i being cubed. So all you have to do in this equation here, for a, you plug in the number 2. For b, you plug in the number 2i. And that's what this is right here. This is the expansion of 2 plus 2i cubed. And when you also have to recall one little tidbit here. When you're cubing I, rewrite it as I times I squared. And of course, I squared is -1. So when you multiply it all out, I cubed is minus I. All right. Now, doing the same for 2 plus 2i cubed, you get 16i minus 16 is what 2 plus 2i cubed is. And when you do it for 2 minus 2i cubed, you got minus 16 minus 16i. Now remember, one of these terms is going to be the apple and one of them is going to be the pear. And we know that the answer says the difference between the apple cubed and the pear cubed is 32i. So just subtracting one from the other to see what we get. You can easily determine by trial and error that the apple is 2 plus 2i, the pear is 2 minus 2i, and if you switch them around, it will not solve equation 3 in the original problem. So it does matter which one is which, and I know a couple of you people were banging your heads against the wall saying you couldn't do it. This is how the problem is solved, and I hope you found it at least a little bit interesting, and I'll see you guys out there.